Hi everybody, here we are on 9.3, chugging right along. This chapter actually has like 10 sections, so we're going to try to do one section per day. It's going to last us about a month getting through all this series stuff. Remember, so series is like the next biggest topic in calculus, right, after derivatives and integrals. So basically what we're doing so far is just trying to figure out if series converge or diverge, and what you've learned so far is the geometric series, right? If it's geometric, meaning it has the form a r to the n, and if r was between 0 and 1, then it would converge, and if r was greater than 1, then it diverged. You also learned the nth term test, which is said, if you're trying to sum an, then if the limit as n goes to infinity of an does not equal 0, then the series will not converge, right? It's just this test for divergence. It's like you take the limit. If it's not 0, then it definitely diverges. If it does equal 0, then you're not quite sure yet, but at least you know when things diverge for sure. So today we're learning another test. It's called the integral test. It's gonna start involving some calculus. There are some conditions involved that we need to check before we ever do this. F must be, so the terms, basically what it's saying here is the terms must be positive. The function must be continuous, meaning no asymptotes or holes or anything, and it must be decreasing for all values greater than 1, for all x values greater than 1. And then what this says is simply that explicit formula that gives us the terms in the sequence is going to be defined as a function. The only difference here between an and fn is an, remember, is only defined at integer values of n, whereas f of n is defined everywhere, right? So f of n you could plug in 1.2, 1.3, 1.4, whereas an you're only going to plug in 1 and 2, and so on and so forth. But what it's saying is if that continuous function converges, then the sum of the explicit series converges. However, important note down here, that does not mean they have the same value, right? All it's doing is saying either it converges or diverges, but it's not going to tell you what the value of it is. Okay, so let's look at an example. Example A here is this. The first thing we need to do is actually test to make sure that this function is positive, right? So let's plug in let's just do some numbers. A1, plug in 1, you're going to get 1 over 2. A2, like the second term, is going to be 1 over 5. And you can think about this. If I'm plugging in x numbers greater than 1, like 1, 2, 3, 4, there's no way to get a negative number here, right? Like there's no subtraction going on, there's no negative sign. So yes, A is positive. So let's just make a little checklist here for ourselves. Positive, yes. Continuous, remember we're going to define a function f of n that equals n over n squared plus 1. And I need to ask myself, is this function continuous? Well, what makes a function discontinuous? It's when the denominator equals 0, or it's outside the domain of the function. But let's look at this. Is there any way to make this denominator 0? The only thing that might work would be, negative 1. Here's the surefire way to do it, right? Let's just go and set the denominator equal to 0 and ask, well, when does my denominator equal 0? Well, it's when n equals plus or minus the square root of negative 1, which negative 1 is an imaginary number. Of course, the square root of negative 1 is an imaginary number. So basically, the denominator will never be 0, which means that there are no asymptotes. So it's continuous. And the last thing we need to show, which is the more difficult part, is it decreasing? So basically what that is we need to take the derivative and show that the derivative is negative, right? The rate of change is negative always. All right, so here we go. We're going to check for decreasing, right? We're going to take the derivative, f prime of n. You're going to need to use a little quotient rule here. It's going to be 1 times n squared plus 1 minus 2n times n over n squared plus 1 squared. do some simplification. This is 2n squared. So we have n squared minus 2n squared, which is negative n squared plus 1 over n squared plus 1 squared. And we have to show that if it's always decreasing, then the derivative will always be less than 0. So we need to show that this is always negative when x is greater than 1, right? That's this. X is greater than or equal to 1. That's this guy up here. Okay, so is it always negative? So plugging in, like, 1, 2, 3, 4. What you can see is if you plug in positive numbers, it's always going to be, and greater than 1, right? So if you plug in 1, you're going to get 0, right? If you plug in 1, you're going to get 0. If you plug in 2, you're going to get negative 4 plus 1, which is negative, over, this is always positive. If you plug in 3, it's going to be negative. If you plug in 4, it's going to be negative. And so you can kind of see that this will always, for n's greater than 1, this will always give me a negative number. So check number 3 is decreasing because the derivative is always less than 0. So all 3 conditions have been met. So now I'm ready to apply this test, right? So the test says that if the integral from 1 to infinity of the function converges, then the series 1 to infinity also converges, right? So what we're trying to do is set up this integral from 1 to infinity of n over n squared plus 1 Zn. And you know what, a lot of times they go ahead and just change these to x's, just, the variable doesn't matter, so let's just make our life easier. Change that to x. And then we have to remember from improper integrals, how do I evaluate this improper integral? Well, we're going to say the limit as n goes to infinity, or let's say a, like that. All right, we just replace that top letter with that infinity with a letter, and then take the limit as that letter approaches infinity. We're going to integrate this. It's going to require some u sub. So u is going to be x squared plus 1. Du is going to be 2x dx. Therefore, dx is du over 2x. Okay, so limit a goes to infinity, 1 to a. It's going to be 1 over u, and then dx is du over, sorry, this is x, du over 2x, and so these x's will cancel, and you're left with that 1/2 there. So this turns into limit as a goes to infinity. Let's bring the 1/2 outside. 1 to a, 1 over u du, and the integral of 1 over u du is natural log. So this will be natural log u, but remember u was x squared plus 1. Let's go ahead and resub that in right here, x squared plus 1. And then this will be evaluated from 1 to a, right? And then we can go ahead and plug in the a and the 1. So this is going to be 1/2 natural log, sorry, limit a goes to infinity, 1/2 natural log of a squared plus 1, absolute values, minus 1/2 ln 1 squared plus 1. We're taking the limit of this entire thing. So what's the limit of 1/2 natural log a squared plus 1? Well, that's like direct substitution. A to infinity squared is infinity. Natural log of infinity is basically infinity minus natural log of 2, which doesn't matter, right? This is 1/2 natural log of 2. This goes to infinity, which means it diverges, right? And so what we would say is, since the integral diverges, then the series also diverges. So we're going to say the series that we're given on the top diverges because the integral diverges. All right, so here's another example. Again, we need to check the conditions, that the conditions are met. So let's check those. One, let's check for positive. So we're thinking, is there any way to plug in a number, you know, for x greater than 1, for n greater than 1 in this case, is there any way to plug in a number and get a negative number? So you could plug in 1, you're going to get 2, 3, you know, all these things. There's no way to get a negative number out of this. So positive, yes. 2, continuous. Remember, we're going to define f of n as 1 over n squared plus 1. Continuous, is there any way to make the denominator 0? Well, it's the same denominator as before, so no, you can't make the denominator 0. So good, it's continuous. 3, decreasing, which again, to check decreasing, we're going to need to take the derivative. So we're going to let f of x equal 1 over n x squared plus 1. Yes, I'm changing the variable, just, you know, it doesn't really matter what the variable is. Therefore, f prime is 0 times x squared plus 1, using quotient rule, right, minus 2x times 1 over x squared plus 1 squared. So f prime of x is negative 2x over x squared plus 1 squared. And we're looking at this and we're asking, we want f prime of x to be less than or equal to 0 for all x is greater than 1, right? So we could plug in 1, 2, 3, and notice that the bottom is always positive, and if you're plugging in positive numbers to the top, it will always be negative. And so yes, f, because f is always decreasing for x greater than or equal to 1, since f prime of x is less than 0, right? It's always negative. So decreasing, yes. Okay, so 3 conditions are met. Now we can apply our integral test. So the integral test, we're going to go from 1 to infinity of 1 over x squared plus 1 dx. And then to evaluate this, we take the limit as n goes to infinity from 1 to a. Sorry, I did that again. Let's not do n, let's do a. Like a goes to infinity of 1 over x squared plus 1 dx. I don't know if you recognize this. This is arctan. So when we integrate, we're going to get arctan, or tan inverse x, evaluated from 1 to a, which basically becomes tan inverse of a minus tan inverse of 1, and we're still taking the limit as a goes to infinity. And we're asking, okay, what happens to the tan inverse as a goes to infinity? Well, if you know what tan inverse looks like this. It has 2 horizontal asymptotes. This one's at negative pi over 2, and this one's at pi over 2. So as this goes to infinity, the y value goes to pi over 2, and then tan inverse of 1 is, remember we're asking tangent of what angle gives me 1. Well, it's when, and tangent is sine over cosine, right? So it's when the sine is equal to the cosine. So the only time the sine is equal to the cosine is at pi over 4. So this guy is pi over 4. And we do these, pi over 2 minus pi over 4 is pi over 4. And so this limit equals pi over 4. However, so we're going to say, I shouldn't be using equals, right? I should be using converges to. That does not mean the series converges to pi over 4, right? That simply means that the series converges, right? The series converges. So this is the integral. The series converges. We'd have to do some other tests to figure out what it converges to. All right, so again, it just tells us, this test tells us whether it converges or diverges, but it will not tell us what the series converges to. All right, let's move on to p-series and harmonic series. Later, we're going to be talking about these things called Maclaurin and Taylor series. You don't have to worry about those yet, but this, what we do right now, is the foundation for that. And we've actually talked about this p-series a little bit, right? So the p-series is the series of summing 1 to infinity of 1 over n to the p, right? So what this is imagine if I just start plugging in numbers, we're going to get 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p plus 1 over 4 to the p, right, like that. And this is our first term, second term, third term, fourth term, so on and so forth. All right, so that's the p-series. And if you can recognize something as a p-series, then you can easily determine if it converges or diverges. So, simply put, it converges if your p is greater than 1. So, such as 1.1, 1.2, 1.3, 1.5, 2, 3, 4, 5, 100, so on and so forth, right? And it diverges if p is between 0 and 1. It's kind of like the opposite of the geometric series, right? So it diverges if you have a fraction or some number less than 1, all right? And then there's this very special case when p is exactly 1. It's called the harmonic series. For those of you who are in music, you've surely heard of this. The harmonic series does diverge, but it has a lot of implications for music. And if you're interested in what that means, you can look at this video here. It has some really interesting, talks about some interesting things, and that will help. Just so you can see, the harmonic series is when you plug in 1, you get 1 over 1. That's like a whole string, right? If you plug in 2, you get 1 over 2, and 3 would be 1/3, 4 would be 1/4, 1/5. And basically, it's like, if you think about in brief, from my understanding of it, is if you had like a whole string like this, you can create the notes by basically cutting the string in half, and then, in thirds and fourths and so on and so forth, like that. So let's do some examples of convergence or divergence. Again, there's no thing here telling us what they converge to, but so we're looking at this, and this is a p-series because it's 1 over n to the p, right? It's like that. We have to look at p. In this case, p is 2, and since p is greater than 1, the series converges. Right? Now, to figure out what it converges to, you would need to actually do some math, right? Next one is this one. Again, here's p. P is 1.1, and which is greater than 1. So this series also converges. To what? You'd have to do something else, like take the partial sums and do all that stuff, which is probably really complicated with that one. For part C, we're looking at n to the -3/2, which doesn't look like a p-series unless you write it as 1 over n to the 3/2, in which case p is 3/2, right? And if p is 3/2, then that's greater than 1, so this series also converges. And lastly, we have this here, which you would just need to rewrite it again. Sometimes it's just rewriting a little bit. We're going to get 1 over n to the 5/2, right? The radical is a half. And again, this is greater than 1, right? P equals 5/2, which is greater than 1. So this also converges. Let's look at another one real quick, just to give you an example of one that diverges. Here's a good one in the book here. It looks like this. We're going from n equals 2 to infinity 1 over n natural log n. And we want to know, does this converge or diverge? So what we need to do first is try to write it as a p-series. Sorry, I'm looking at the book now, and this is not a p-series problem. We would use integral test on this. So a p-series that might not converge would be, let's say, like 1 over square root of n, right? And then you could write this as, you could write this as 1 over n to the 1/2, and because 1/2 is less than 1, and like that, this one would diverge, right? So, and this is a good example of, if you did that test, the nth term test, you would get 0, right? You get 0, which again tells you that in that test, if we got anything other than 0, we would say that this series diverges, right? But in this case, we get 0, but the thing still diverges, right? So just because in the nth term test, just because you get 0 in the nth term test does not mean that it will diverge. You have to do some other test, which in this case, you can do the p-series test to see that it diverges, right? So that's just a good example of one where the nth term goes to 0, but it still diverges. All right, so your homework is here, right? Ask lots of questions, talk to each other a lot.